Hello guys, let's learn physics in a much simpler way than you might think at first. So come on and let's carry out a simple experiment. For this, just grab simple things that can be found at home. For example, a clear and empty plastic bottle that should be filled with water. I have already filled it with water. And a so-called dropper with a squishy rubber balloon part, which will be also important during the experiment, and the dropper should be also filled with water, just like this, at a 1/4 part of the uh, glass tube of the dropper. Then the dropper should be placed inside the water bottle, just like this. And no matter that some water will flow out of the water bottle, but what do we see at the moment? Just like in the case of this organization with the same dropper, but I also marked it with uh, some insulation tape for better visibility. The dropper stands in a rather stable way on the top of the bottle. But why? Let's see it. On this small figure, you can see the organization of our scientific experiment. As you can see, the dropper is placed on the top of the bottle, which is filled with water completely. There is some air inside the glass tube of the dropper, and there is water inside, also inside the glass tube of the dropper. Both the air and the water stands in a rather of an equilibrium, which both parts has their volumes. For example, the air has its volume 0, V0, and the water has its own volume. It is marked with V1, and it is also has a mass of Mi. So M, or to be correct, mass internal or internal mass. And there is also should be mentioned a volume to be extracted, which is marked with Vx, that comes out of the dropper due to the internal pressure of the air bubble inside the dropper. Note that the pressure inside the dropper is the same as the atmospheric pressure. But now let's give some load on the bottles, on both bottles. Let's press them on their sides. What do we see? The droppers inside the bottle began sinking immediately, and I really hope that the camera is able to see uh, the water inside the uh, dropper moving as it is moving its so-called meniscus curve, as it constantly changes its shape. When we press the bottle side of the bottles, the mm, the water's level's meniscus curve inside the dropper has a convex shape, and when we release the pressure inside of the bottles, the meniscus curve has a concave shape, as the water as we know, is a wetting liquid. And we also know that liquids can be squeezed, and but the air or gases can be squeezed. So when the water rises inside the droppers glass tubes, the air is simply squeezed, and there the mass of the system with the water, the air inside the glass tube, and the uh, droppers themselves begin immediately sinking. And let's see its figures. So what do we see on this figure? We might see the squashed water bottle filled with water with an F force, but we unfortunately we can't measure the force which is produced by our fingers and our hands. Uh, so it is only marked with an F, and uh, it and this force uh, ends up in a different difference in the pressure, and or to be correct, in a change in the pressure, which is marked with delta P. And that's why you can see the water flow inside the water tube of and the glass tube of the dropper itself. So the volume of the air bubble changes immediately, and the volume of the water uh, and also the mass of the water is also changing. Whether we like calculations or not, but physics can't be imagined without any kind of calculations, as we would like to know the exact measurements and quantities of the different kind of elements and liquids that took part in this in these effects. And that's why I wrote all the most important calculation formulas for this scientific experiment. This equation describes the equilibrium when the dropper is on the top of the water bottle in and the water level and the air bubble inside the dropper is can be found in a equilibrium, just like on this small picture. And when we when we try to give some load on the bottles sides, the the volume of the different parts, for example, the air part and the water part, changes. And note that the equation mark, it differs from the equilibrium's equation mark, because the changes themselves of the volume changes themselves are very small, and only can be calculated with the help of differential equations, and these would be rather difficult to estimate the correct results. And unfortunately, I also don't have any kind of force measuring device in order to measure the force being produced by my fingers and my hands on the sides of the bottle. And when we divide the main equilibrium of this experiment, we get these smaller equations. And note that we in case of both cases, we get the glass parts, or to be correct, the empty droppers mass as a result. And we also can say that the water to be extracted during the pressure during the pressure on the side of the bottle can be described with the volume changing volume, or the delta V. And with the help of these quantities, we can also describe the pressure difference for to be used for sinking this small dropper, and with the help of the density, the gravitational acceleration, and the original volume of the air bottle, and the volume change, or to be correct, the water to be extracted, and the atmospheric pressure, we can also calculate the critical haze or critical depths inside the water bottle when the dropper begins to sink, and the H crit describes the critical water level on inside the glass tube of the dropper when the dropper begins sinking. And this and during this experiment, we created a so-called Cartesian diver named after Renatus Cartesius, or to be correct, in his original French name, René Descartes. If you like this small video, then share it and hit the like button, and don't forget to subscribe. See you later, and see you next time.